Hi, it's Rick McMaster again. Welcome to part 2 of How Cold is Cold. This time we'll take a look at some material properties at lower temperatures. We'll start outside at our IBM campus in Austin, Texas. Today it's about 86 degrees Fahrenheit or 30 degrees Celsius or 303 Kelvin. Wait, so what will happen when I throw the liquid nitrogen in the air? See you in a few minutes. Almost all of the liquid nitrogen was gone by the time it would hit me or the ground. Let's try that again. Notice that some drops do make it onto the surface of the water, but they float. Liquid nitrogen has a specific gravity of about 0.8. That is, it has about 80% of the density of water at standard temperature and pressure. Remember that we talked about density in part 1. So we have pools of liquid nitrogen that float on the surface of the water. They cool the atmosphere locally, making the clouds that we see. Let's go back inside to look at some other properties of materials at 77 Kelvin. Let's talk a little bit more about liquid nitrogen. As you remember from our last video, it boils at 77 Kelvin, negative 196 Celsius, or negative 321 Fahrenheit. If you notice as I dip the cup in, I'm very careful not to have my hand in contact with the liquid nitrogen. But yet I can hold this styrofoam cup very comfortably when the liquid nitrogen is inside. So two questions for you. First, what's the difference between the boiling liquid nitrogen inside the cup and my body, my hand? I'm feeling well today. That's a hint. The other question for you is, how is it that I can manage to hold something that is so much colder than my hand in this cup? To answer the first question, air is an excellent thermal insulator, and styrofoam is made mostly of air. Plastic as well is a very poor thermal conductor. In terms of the second question, I'm feeling well today. My temperature is 37 degrees Celsius. The inside of the cup is 77. So if I look at the difference between the two, 77 Kelvin to 310 Kelvin, there's a thermal gradient of almost 233 degrees across the 1/8 inch of styrofoam. Let's take a look at some liquid nitrogen. Let's take a look at what happens when I dump just a little bit of liquid nitrogen on a piece of carpet. As you can see, the liquid nitrogen immediately evaporates. Now remember, room temperature is almost 200 degrees Celsius higher than the boiling point of liquid nitrogen. Let's take a little bit of liquid nitrogen and dump it into a transparent bag. Okay, as you can see, the liquid nitrogen is a clear, colorless liquid that is boiling in the bag. Notice that every once in a while there's a small drip that comes off the end of the bag. The bag isn't leaking. That's oxygen that's liquefying from the atmosphere and dripping off the outside of the bag. Remember that liquid oxygen is 90 degrees Kelvin and liquid nitrogen 77. So what we see dripping is just liquid oxygen, and it immediately evaporates as soon as it hits the tabletop. Let me prove to you that it is indeed boiling, that in the last time I just didn't accidentally put some soda inside a bag. I have a piece of scientific apparatus known as a whistling metal tea kettle. I'm going to add the liquid nitrogen, put the top on, and close the teapot. As you can see, the teapot immediately starts to whistle because the teapot was at room temperature, and the liquid nitrogen boils at almost 200 degrees lower. Now I do need to be very careful because, as you can see, the teapot has become very, very cold. Metals transfer heat very quickly, so I dare not to touch that. And when we're done, we can just dump out our liquid nitrogen. Let's look briefly at some properties of liquid nitrogen. As I have mentioned several times, its boiling point is approximately 77 Kelvin at 1 atmosphere. Its melting point at 1 atmosphere is about 63 K. Its density is 0.8 grams per cubic centimeter. It is a clear, colorless liquid, and you can see why through its spectral lines where no specific color dominates. We'll talk about its expansion ratio shortly. And finally, the heat required to take 1 mole of nitrogen from a liquid to a gas is 5.56 kilojoules. While this is much less than water at 40.65 kilojoules, it is more than enough to cause severe damage to tissue that comes in contact with it. Okay, now it's time to put you to work. We have 2 bags, sealable, of different sizes. We have some chocolate milk. You don't have to use chocolate milk. You can use whole milk, add a little sugar or flavoring, whatever you would like, and some salt and some ice. What we're going to do is open our chocolate milk, and we're going to put about a cup in our bag. And we're going to go ahead and seal the bag, getting most of the air out of it. Then we're going to take some of our ice and put it in the larger bag. Put our sealed chocolate milk bag inside there. Add the rest of our ice and a little bit of salt. Salt's added to reduce the melting temperature. And again, we're going to close it up, seal it well. And what I'd like you to do as you continue watching our video and having discussions in your class is just continue to work that around. And it'll take 15 to 20 minutes before you have ice cream, and we'll come back and talk about that a little bit later. So good luck in making your ice cream. Okay, so let's see what happens as liquid nitrogen becomes a gas in a closed environment. We'll take this balloon and put it on the nozzle. We'll take our tube and add just a little bit of liquid nitrogen. And we will put the balloon on top to close the environment. So what's happening? Now let's look at what happens to a certain amount of gas as it warms up from 77 Kelvin to room temperature, about 295 Kelvin. The pressure in a balloon as it expands changes only about 5%, which we'll treat as a constant. N and R are constants. So the volume increase is proportional to the temperature change in Kelvin, about 3.8x. So the total volume expansion is about 700x, or 1 fluid ounce of liquid nitrogen becomes almost 8 gallons of gas at room temperature. Now let's go in the opposite direction. Let's take a balloon and blow it up at room temperature and cool it to 77 K. Discuss in your class what happens and why. Welcome back. Let's see what happens. Let's place the balloon in the liquid nitrogen. The glove does not protect my hands from the liquid itself, but it does protect it from the cold vapors. And as you can see, the balloon is decreasing in volume. So what's inside the balloon? We have nitrogen and oxygen from the atmosphere. less oxygen because our body has used some of it, but our body has introduced carbon dioxide and water vapor to a higher extent than is normally present in the atmosphere. So as the balloon has cooled completely, you can see that it has decreased tremendously in volume. But as it warms back up, it reinflates. So let's look at each one of the components that's inside the balloon. We have water vapor. The water vapor condenses to water and freezes. Net effect is a much smaller volume. The carbon dioxide becomes dry ice, again decreases substantially in volume. The oxygen liquefies at 90 Kelvin and decreases in volume. The nitrogen, some of it liquefies, some of it becomes very cold. The overall net effect is that the balloon decreases substantially in volume, but we have a reversal of the changes of state, and as the balloon warms back up, I'm just accelerating that a little, it reinflates. Let's take a look at a rubber ball made of a similar material to that of the balloon that we just discussed. We're going to take the ball and cool it down to 77 Kelvin. Discuss in your class what you think will happen. We'll be back in just a couple minutes. Okay, let's go ahead and immerse the ball in the liquid nitrogen. As you can see, the liquid nitrogen is boiling furiously. We'll not let it cool down the whole way. Let's just take it off for a moment. Let's see what happens. You can see that it's no longer bouncing the same. It has a much different sound. Now let's take it the whole way down to 77 Kelvin. And I can tell when that occurs when I no longer see the furious boiling around the ball. It is slowing down quite a bit now. Okay, let's try and bounce the ball and see what happens. You can see that it sounds considerably different. Okay, let's take the ball and throw it against the slab. And as you can see, the ball broke into a number of pieces. Here happens to be one of them. So the mechanical properties of the ball changed dramatically at 77 Kelvin. Now if I let this warm back up to room temperature, the flexibility of the rubber will still be there as it was previously. We just have a ball that is in a number of pieces. Okay, for some fun, let's try a couple of vegetables. We have a carrot and we have a pepper. Now the pepper is hollow, so I'm going to hold it underneath. The carrot did sink to the bottom. Here's our carrot. Okay, it does break in pieces. And let's take a few more minutes to let our pepper cool down the whole way. This, by the way, is one of the dangers of liquid nitrogen. It is a cryogenic liquid and can cause extreme frostbite. Remember that our cells, like that of the pepper, like that of the carrot, are made mostly of water. So as the water freezes, it expands and breaks the cell walls, and the cell dies. Let's go ahead. Our pepper is still getting cold. Maybe it's cold enough. Let's go ahead and let's pick up the pepper and let's drop it on our slab. Again, it breaks into pieces because we have frozen the water. Okay, let's take a look at the electrical properties. We're going to investigate three different devices. We have a pure metal in the terms of a small transformer. We have an alloy resistor, and we have a carbon resistor. Now remember, carbon is immediately above silicon in the periodic table and shares some of the same electrical properties with silicon, a semiconductor. Think about your physics. What do you expect to happen to the resistivity of each of these devices as the temperature is lowered from room temperature to 77 Kelvin? See you in a few minutes. Okay, welcome back. Let's take a resistance reading on each one of these devices at room temperature. So we'll start with our transformer, and you can see that it's a little beyond halfway on our range. Now notice in the resistance readings that a high resistance reading is at the far left of the scale and a low resistance reading is at the far right. In fact, we can demonstrate that by shorting these two together. Okay, so that would be essentially zero resistance. Let's move next to the carbon resistor. And the carbon resistor should also read somewhere near the middle of the scale. A little bit higher than our transformer. And then finally, our alloy or precision resistor, again, somewhere near the middle of the scale. Okay, let's start with the alloy resistor. Let's see what happens as we lower its temperature to 77 Kelvin. Okay, as you can see, there is very little change in the resistance, and that's because the resistivity of the alloy is being controlled mainly by the scattering off impurities. And because we have a mixture of two or more metals, the resistance is not changing substantially, and that's important in terms of electrical design because we don't want the electrical properties of our amplifiers, our Blu-ray players, or any other devices like that to change substantially with temperature. Let's move next to the carbon resistor, and again remember the carbon resistor is going to have properties very similar to a semiconductor. And as I lower its temperature to 77 Kelvin, you can see that the resistance is increasing. That's because I'm decreasing the amount of carriers in the band gap. And finally, let's move to our transformer, which represents our pure metal. And let's lower everything down in here. And as you can see, the resistance is becoming less. Now remember, temperature is a measure of the average kinetic energy. And so as I lower the temperature of the copper in the transformer, there are fewer vibrations, and it's the scattering of the electrons off of those vibrations known as phonons that cause the resistance to change. And so I have fewer vibrations or smaller vibrations, and because of that I end up with a lower resistivity. Here are some examples of the resistivity of metals, semiconductors, and alloys. As you can see, the resistivity of metal decreases at lower temperatures. The resistivity of semiconductors increases at lower temperatures, and the resistivity of alloys is nearly constant. Now let's talk about an interesting property of superconductors called the Meissner Effect. We're going to start with a ceramic, which is an insulator at room temperatures, but becomes a superconductor at liquid nitrogen temperature. So we're cooling the ceramic down to 77 Kelvin. As a superconductor, it has almost no resistance to the flow of electrical current and allows very little magnetic flux to penetrate its surface. We have a very, very small magnet here which will cause an eddy current on the surface, essentially making a mirror image of the magnet. So this magnet should, if we're careful, float above the surface. And you can see I'm spinning it there. So that's actually floating above the surface. Discuss in your class what some applications of this might be, and we'll see you in a few minutes. A small eddy current is produced at the surface of the superconductor that gives the appearance of a mirror image magnet below the surface of the superconductor that repels the magnet above the superconductor. Okay, let's have some fun and see how fast we can make some ice cream. If you've ever made ice cream at home, or maybe even in your classroom, you know that it can take anywhere between 15 minutes or an hour or more. We're going to see how quickly we can make some ice cream here. We're going to start with some heavy cream. We'll go ahead and turn our mixer on slow. We're going to add some Nesquik for some chocolate flavor. And then to make it even more flavorful, we're going to add some cookies. We'll make sure that those get broken up well. Okay. So again, normally we would expect ice cream to take anywhere between 15 minutes and maybe even an hour and a half. We're going to see if we can do it in considerably less time. Hopefully you have a clock or some way to time this in the classroom, and let's see how fast we can make it. So let's add some liquid nitrogen. And we'll add just a little bit more. And you can hear that the mixer is struggling a little bit more. And we have ice cream. Okay, we're going to take a minute here and ask for a volunteer to come up and sample a little bit of it. So let me introduce you to Troy, who's been doing our photography here, and ask him to sample our ice cream. Good ice cream.
Awesome ice cream.
Okay, so ice cream in about 30 seconds. I've had a lot of experience in dealing with cryogenic liquids, so it's important to talk about the cautions you need to take in handling liquid nitrogen. First, liquid nitrogen is very, very cold and can cause irreversible frostbite in a very short period of time. Delicate tissues such as your eyes can be damaged even more quickly. Second, if you are in a closed environment, the percentage of oxygen decreases as the liquid nitrogen boils off. Because the nitrogen gas is cold, the oxygen level close to the floor will be lower. At 10% oxygen, you will pass out, and if the percentage of oxygen is lower, you will die of asphyxiation. Finally, you remember that from a liquid to room temperature gas, nitrogen expands about 700 times in volume. This pressure buildup can cause closed vessels containing liquid nitrogen to build up pressure and rupture explosively. It's magic. Okay. Hi, and welcome to the Teacher's Guide to this video. Part 2 of How Cold is Cold picks up where Part 1 ended and concentrates on the property of materials at low temperatures. It can be used independent of Part 1 with the assumption that the Kelvin temperature scale is understood with points such as room temperature, body temperature, and boiling points of some cryogenic liquids, including liquid nitrogen. Segment 1 starts with liquid nitrogen being thrown in the air with the question, what will happen? Left for you to discuss with the class. With the outside air temperature greater than 300 K, almost all the liquid nitrogen will become a gas, condensing water vapor and leaving trails behind the liquid nitrogen droplets as they evaporate. While some of the liquid nitrogen does fall back down, I am protected by my cap and lab coat from any direct contact. Segment 2 starts with the liquid nitrogen being thrown into the air twice and then dumped into the reflecting pool. Reference is made to density, which was briefly discussed at the start of part 1. The video then moves back inside with a review of the temperature of liquid nitrogen and ends with 2 questions. First, what is the temperature difference across the 3 mm thick styrofoam cup, and why isn't my hand freezing? The answer to the first is 310 K body temperature minus 77 K liquid nitrogen, or 233 Kelvin or Celsius degrees. You may also want to discuss the temperature difference in Fahrenheit degrees. Ask the students which gradient is bigger, liquid nitrogen in the cup or very hot tea or coffee. Even with boiling water inside the cup, the temperature difference is only 63 Kelvin, considerably less than the difference with liquid nitrogen in the cup. The plastic in the cup and incorporated air makes the styrofoam an excellent thermal insulator. Left alone, the cup will begin to frost and ice on the outside since there is only the surrounding atmosphere to maintain some temperature gradient across the styrofoam. Segment 3 introduces some additional properties of liquid nitrogen. It reinforces a point from part 1, that metals transfer heat very quickly. You can end this segment with a discussion of how these properties compare to water. Segment 4 is optional and should only be used if you plan to have the students make ice cream in the classroom. The segment is located here so that, if used, the ice cream will be ready at the end of the overall session. For each team of students, you will need 2 different sized heavy-duty bags, such as freezer bags that can be sealed. A 1 quart and 1 gallon bag work well. 1/2 to 1 cup of flavored whole milk is put in the inner bag and sealed with most of the air released. I don't recommend using over 1 cup because the time to make the ice cream will be too long. Some ice should be placed in the outer bag, then add the smaller bag, and then add more ice around the bag, the inner bag. More can be added later if needed. Add approximately 1/4 cup of salt to the bag and seal it with most of the air released. The bag should be worked between the hands gently to avoid breaking the bag. If you have teams of students doing the activity, they can pass the bags among themselves, which also avoids their hands getting too cold. Segment 5 demonstrates what happens to liquid nitrogen in a closed environment. Segment 6 starts with a discussion of the expansion. The phase change of liquid to gas at 77 K gives an expansion of approximately 1 to 200. As the gas warms from 77 K to room temperature, another factor of 3.8 is introduced. The ideal gas law is used to calculate the latter factor. I then ask the question, what happens to a balloon when it is in contact with the liquid nitrogen? Use this as an opportunity to discuss the components of the atmosphere and what is introduced in higher amounts in blowing up the balloon. You can then discuss what happens to each of the components as their temperature is lowered to near 77 K. The water vapor, the carbon dioxide, the oxygen, and the nitrogen. Students may suggest other components that they saw listed in part 1, so be prepared to talk about how much of each is contained in the atmosphere. Segment 7 starts with freezing the balloon and allowing it to return to room temperature. I then ask the question about what will happen to a hollow rubber ball that is frozen to 77 K. Elements of your discussion can include the mechanical properties of the rubber ball, including the sound that it makes when dropped. You should also discuss what happens to the gases inside the ball and the partial vacuum that results when the ball's temperature is lowered. Segment 8 demonstrates what happens when the ball is frozen and relates the freezing of a carrot and pepper to frostbite. It then moves on to the temperature dependence of the resistivity of metals, alloys, and superconductors. The class discussion is centered around what will happen to each resistance from room temperature to 77 Kelvin. Segment 9 shows what will happen to each, and some examples of metals, semiconductors, and alloys is shown. The data can be used for classroom exercise in determining the resistivity of each at 77K. Then, a ceramic superconductor is used to demonstrate the Meissner Effect. The question for a class discussion is the application of superconductors. Several references are provided in the materials available on the Blossoms webpage for this lecture. Segment 10 shows a diagram of the Meissner Effect and then moves on to making ice cream using liquid nitrogen to cool the mixture in about 30 seconds to the ice cream consistency. If you have had the students making ice cream in the classroom using the procedure described in segment 4, you can have them open the bags and sample the ice cream. They can also compare the time that it took for them to make the ice cream to me making ice cream in the video. The segment ends by summarizing the cautions needed in handling liquid nitrogen. If you decide to bring liquid nitrogen into the classroom to repeat any of these demonstrations, please be careful in doing them. When I do this in a classroom, I work behind plexiglass that shields the audience from the demonstrations. Please contact me through the Blossoms website if you have any suggestions or questions. Thank you.